In the early morning light of the Tunisian desert, a single American gun crew realized that 20 years of military planning had just failed them. The year was 1943. They were positioned behind a 37mm anti-tank gun, a weapon the army had assured them was the finest of its class. As a German panzer lumbered toward their position, the loader slammed a 2-pound projectile into the breech. The gunner, a man we will call the Tunisian tanker, sighted the target and pulled the firing lanyard. The shell struck the front of the German tank with a sharp metallic crack, but it did not bite. It sparked and ricocheted into the air like a pebble hitting a wall. He fired again, and then a third time. To his horror, the German machine did not even pause. It simply corrected its course and kept coming. That soldier had done everything he was trained to do. He had achieved a direct hit on an advancing enemy, but the tool in his hands was a toy compared to the threat in front of him. This moment at Kasserine Pass was the brutal endpoint of a 20-year argument conducted in quiet offices thousands of miles away. It leads us to a question that seems impossible given the eventual outcome of the conflict. How did a broken bureaucracy build the weapons that won the war? To understand how an army enters a desert with toys instead of tools, we must look back to the silence of 1919. The First World War had just ended, and the United States Army was trying to figure out what the next conflict would look like. General Westervelt convened a board of 7 officers to map out the future of American ordnance. They were forward-thinking men who studied ballistics and concluded that the future was entirely motorized. They wanted a family of guns that could move as fast as a truck and fire shells that could penetrate any armor then in existence. The Westervelt board report became the definitive roadmap for the Ordnance Department, but it was a plan built for a world that the American public wanted to forget. Vision is expensive, and the United States was entering a period of profound isolationism and fiscal restraint. In 1920, Congress passed the National Defense Act, a piece of legislation that would effectively paralyze American tank development for 2 decades. This law abolished the Tank Corps as an independent branch and legally shackled all tank development to the infantry. A tank was no longer a weapon of independent maneuver, it was now a mobile shield for a man with a rifle. Because the infantry branch dictated the requirements, they demanded machines that were light, slow, and easy to transport. They insisted on a weight limit of 15 tons. 15 tons was the maximum capacity of the standard Army pontoon bridge and the existing highway system of the 1920s. The military was not building weapons to defeat an enemy. They were building weapons to fit their own infrastructure. General Gladion Barnes, a pragmatic innovator who would spend his career fighting this kind of red tape, saw the disaster coming. He knew that physics did not care about the weight capacity of a wooden bridge. If the enemy built a 30-ton tank, a 15-ton American tank would simply be a steel coffin. But the bureaucracy was absolute. For 2 decades, engineers were forced to design weapons that fit the bridges, rather than weapons that won the battles. This created a culture of perfection on paper. During the 1920s and 30s, the annual research budget for tanks averaged roughly $60,000. For perspective, a single commercial giant like General Motors was spending $20 million on research in the same period. The Ordnance Department became a collection of small, isolated arsenals where engineers spent years tinkering with prototypes that never went into production. They were trapped in a cycle where a single 2-page directive from 1922 governed every decision they made. By the time the first shots were fired in the Tunisian sand, the gap between the law and reality was a mile wide. The engineers had spent 20 years perfecting a 37mm gun because it was light enough for 4 men to wheel across a field. It was a masterpiece of portability that was entirely useless against a modern tank. The law had been followed, but the soldiers were not safe. In 1922, a short directive from the General Staff effectively halted the evolution of American armored warfare. It was not a document about strategy, it was a document about bridges. With a single administrative stroke, blueprints for heavy machines became illegal. Designers were forced to literally erase armor and firepower to meet a logistical number. This obsession with weight limits created a technological ceiling that the United States would not break for nearly 20 years. While other nations were experimenting with 40-ton monsters, American engineers were trapped in a cycle of micro-designing motorized tin boxes. While the bureaucracy was busy measuring bridges, the intelligence coming from overseas was becoming increasingly desperate. Because the government refused to fund formal technical espionage, the army had to rely on the personal initiative of its observers. One such officer, the Stockholm sketcher, found himself at a high society gala in Sweden, surrounded by foreign military attaches. He knew that the Swedish artillery breaches were years ahead of anything in the American inventory, but he had no way to legally obtain the specifications. During a lull in the dinner, he sat in a corner and frantically drew the mechanical details of a new cannon breech onto linen napkins. He hid the napkins in his jacket to bypass export bans. This was how the United States gathered its technical data in the 30s. Knowledge was not gained through industrial cooperation, but through sketches on dinner napkins. The most significant black hole in American development was not a lack of intelligence, it was a personality. J. Walter Christie was a brilliant, erratic, and deeply combative inventor who believed he had solved the problem of tank mobility. In 1929, Christie staged a demonstration for the American Automobile Association that looked more like a stunt than a military trial. He produced a vehicle that could run on tracks across broken ground, but could also shed those tracks and run on rubber tires like a race car. On a paved road, his machine hit 69 miles per hour. It was a mechanical marvel that mocked every weight limit the Army held dear. But Christie refused to cooperate with the bureaucrats he despised, and the Army refused to trust a man they could not control. While the world moved toward war, the best tank suspension in existence sat in a warehouse because two sides could not agree on a contract. To the journalists and politicians watching the trials, it looked like the future was arriving on rubber tires. They saw a tank that could rush to a battlefield at highway speeds before diving into the mud. But inside the Ordnance Department, the reaction was cold and skeptical. Gladion Barnes and his fellow officers looked past the speed and saw a machine that would be a nightmare for any mechanic. The vehicle had no guns, no armor, and no space for a radio or a crew. J. Walter Christie had created a suspension system of coil springs that allowed the tank to jump over obstacles, but the man himself was impossible to work with. He viewed any request for a change as a personal insult to his genius. He refused to provide blueprints, ignored safety requirements, and treated procurement officers with open contempt. The genius refused to be a partner. This clash of egos resulted in a decade of deadlock. The Army wanted the suspension, but they did not want the man who designed it. They spent years in a bitter struggle over patents and prototypes, while the development of a real combat tank sat in a drawer. Because the high-speed concept became a public sensation, it siphoned away the small amount of research funds that should have gone toward armor and firepower. The military became obsessed with the idea that a tank should be a race car on weekdays and a tractor on Sundays. Publicity had replaced military priority. While the Americans argued over weight limits and personality clashes, a shadow was falling over Europe. The German high command was not worried about whether their tanks would break a wooden bridge. They were simply building the bridges to carry the tanks. They took the very suspension ideas that Christie had pioneered and turned them into a doctrine of mass and speed. Washington was building a compromise. By the time the United States finally abandoned the 15-ton limit and the high-speed fantasy in the late 1930s, the lost decade had done its damage. The Army had plenty of blueprints for fast cars, but they had not built a single modern tank that could survive a slugging match. The bureaucracy had succeeded in protecting the bridges, but they had ensured that the first generation of American tankers would go into battle in machines designed for a highway. The Army never bought the man, but the comfortable isolation of Washington was about to be shattered. In the early summer of 1940, frantic cables began arriving from across the Atlantic. For 20 years, the American military establishment had assumed they had all the time in the world to perfect their designs. They treated the gathering storm as a theoretical problem to be solved with committee meetings and slow trials at the proving grounds. As the German army swept through France in 6 weeks, the realization hit the general staff like a physical blow. The American army was already obsolete. To understand the panic of that moment, you have to look at the intelligence machinery that was supposed to be the nation's eyes and ears. It was paralyzed by a culture of indifference. Information about German tank tactics and the power of their new artillery was not missing. It was simply being ignored. Reports from foreign observers were treated as noise rather than news. In the offices of military intelligence, stacks of technical descriptions were processed by officers who would apply a stamp and file them away in basement cabinets. The system protected the status quo. The volume of paper passing through Washington in that summer of anxiety was immense. Amidst the dinner party gossip and diplomatic pleasantries, there were genuine warnings. In a candlelit air raid shelter in London, the London Observer scrawled frantic notes about the wreckage of British armour he had seen in the fields of Flanders. He described how the standard anti-tank guns were being brushed aside by German panzers, as if they were made of cardboard. He tried to tell his superiors that American doctrine was a fantasy, but his notes were just more paper in a system that was not ready to read them. The warning was written in the dark. The divide between the two worlds was total. On one side was the country club atmosphere of the peacetime army, where the primary concern was whether a tank would damage a local highway. On the other was the brutal reality of the lightning war. The Americans were still debating the merits of the 37mm gun, while the Germans were fielding weapons that made it look like a museum piece. A few innovators began breaking rules. This is the part of the story that most accounts skip because it does not happen on a battlefield. It happens on a firing range at the Aberdeen Proving Ground. In late 1940, a Swiss inventor named Henry Mohupt arrived with a device that looked like a simple metal cone. He claimed he had perfected a hollow charge. This was a way of shaping an explosive blast so that it could burn through steel rather than just blowing up against it. He carried the secret in a box. Under normal circumstances, Mohupt would have been caught in a 2-year cycle of testing and bureaucratic review. But the pressure of the war in Europe had finally reached a boiling point. General Gladian Barnes, who had spent years fighting the slow consensus of the boards, saw the potential in the work of the inventor. He pushed for an immediate demonstration. Barnes was done waiting for permission. The generals gathered at Aberdeen were skeptical. They had been told for years that only a massive high-velocity cannon could knock out a modern tank. Mohupt set up his experimental charge against a slab of shatterproof armor plate. This was the kind of steel that had stopped every bullet and shell in the army's current inventory. When the charge was detonated, it did not just dent the plate. It focused a jet of molten metal that sliced through the steel as if it were soft wax. Mohupt watched the smoke clear to see a perfectly round hole where the impenetrable barrier had been. The heavy armor plate had failed. To understand why this demonstration changed everything, you have to look at how the army usually bought its weapons. They were obsessed with the perfect design that was light, durable, and suited for every environment. Mohupt showed them that a weapon that worked well enough, delivered now, was worth more than a perfect one that arrived 2 years too late. His discovery would eventually become the heart of the bazooka. It gave one soldier tank-killing power. The skepticism in the room evaporated. The generals realized that the old ways of slow, methodical development were a luxury they could no longer afford. The era of the perfect design was over, and the era of the practical weapon had begun. This shift in thinking, led by men like Barnes and civilian scientists like Vannevar Bush, would define the next 4 years. They stopped looking for the ultimate weapon and started looking for the one they could build by the millions. The bureaucracy was finally starting to crumble, but the cold data of the laboratory was about to collide with the heat of the front line. At Fort Churchill, on the frozen rim of the Hudson Bay, the air is so cold that it ceases to be a weather condition and becomes a mechanical problem. In the winter of 1943, a small team of engineers sat in a wooden shack in 30 below zero weather. They were surrounded by some of the most expensive glass in the world. They were not there to fire guns or test armor. They were there to watch grease. The optics had to survive the ice. Now consider the physics of a precision instrument. To aim a heavy cannon at a target 2 miles away, the gears must move with the smoothness of a fine watch. But at these temperatures, the standard lubricants used by the military did not just thicken. They turned into a solid, waxy glue. The Churchill technician spent his days documenting this slow-motion failure. He watched as the precision rangefinders became useless hunks of metal. To prove the optics could survive the thermal shock, he performed a simple, gritty test. He reached out and scraped the rime of ice from a lens with his own fingernails. He needed to see if the glass had cracked. To understand why this mattered, you have to realize that a tank is essentially a blind steel box. The crew's only connection to the outside world is a series of prisms and lenses. If those lenses fogged or the gears froze, the most powerful engine and the thickest armor meant nothing. The soldier was effectively fighting in a dark room. The laboratory designs that had looked so perfect in a heated office were failing once they touched the real world. The Weapons Bureau had to start over. They redesigned the standard service binoculars by adding tiny hidden packets of silica gel. These desiccants acted like a sponge, sucking the moisture out of the air inside the casing before it could condense. They even had to fight their own internal rules. For years, the telescope used by battery commanders had been built with a large, awkward eyepiece designed for a man wearing a gas mask. The engineers finally realized that an observer who could not see the target was a greater liability than an observer without a mask. They stripped the requirement and finally gave the soldiers a clear view. But the cold was only half of the struggle. Thousands of miles away, in the high humidity of the Pacific, teams were fighting life itself. A specific type of fungus began to grow inside the sealed optics of the new rocket launchers. It did not just blur the vision, it actually ate the chemical coatings on the glass. The military was forced to reinvent domestic glass production. They shifted from artisan methods to mass-produced, machine-ground prisms treated with antifungal compounds. They were learning that a weapon is not just a machine, it is a guest in an environment that is trying to destroy it. While the men in the jungle struggled with moisture, the engineers in the States were perfecting a centerpiece of armored technology. The gyrostabilizer was a box of sensors and motors designed to keep a tank's gun level while the vehicle bounced over broken ground. On paper, it gave the crews a massive advantage. It meant they could fire accurately while moving, whereas their enemies had to come to a full stop to aim. It was a masterpiece of engineering, the kind of thing that wins wars in a boardroom. But the blueprints never showed the human reality of the turret. When these stabilizers reached the crews in Sicily and Italy, the men did not see a miracle. They saw a distraction. A tank in combat is a place of incredible noise and vibration, where the air hangs thick with the smell of cordite. The gunners found that the stabilizer made the gun barrel feel unpredictable. They did not trust the hum of the electric motors. One skeptical gunner finally had enough of the mechanism. He took a leather strap from his gear and tied the stabilizer down. He trusted his own hands more than the machine. To understand how these tools reached the front, we have to look back to the summer of 1942. The internal culture of the army was undergoing a forced, painful marriage. For decades, the Ordnance Department had been a closed circle of professional soldiers and career engineers. They believed only a man in uniform could understand the requirements of a weapon. But the scale of the new war required the specialized theoretical brilliance of the American university system. This led to the creation of the National Defense Research Committee. This was a civilian agency designed to bypass the slow-moving military bureaucracy and inject high-level science directly into the production lines. The culture shock was immediate. On one side of the table were colonels who had spent 30 years at the proving grounds. On the other side sat civilian physicists and chemists whom the soldiers called longhairs. The military men wanted rugged simplicity, while the scientists wanted technological leaps. To understand why this friction mattered, you have to look at the development of the proximity fuse. This was essentially a miniature radio station packed into the nose of an artillery shell. It was designed to explode the moment it sensed a target nearby, rather than relying on a mechanical timer. It was one of the most closely guarded secrets of the war, second only to the atomic bomb. This is where the laboratory met the reality of the arsenal. During a high-level meeting, one scientist from the committee clutched a prototype of this fuse like a holy relic. He was explaining the sophisticated theory of wave reflection to a group of skeptical officers. One colonel interrupted the lecture. He did not want to hear about physics. He wanted to know if the device was a toy. He suggested they take the prototype and drop it off the roof of the building to see if it survived the impact. To the scientist, this was a barbaric way to treat a precision instrument. To the soldier, it was the only test that mattered. A weapon that broke on the floor would never survive the blast of a cannon. Eventually, the two sides found a middle ground. The scientists learned to toughen their components, and the military learned to trust the lab. This partnership allowed for the mass production of the proximity fuse, a tool that tripled the lethality of anti-aircraft fire. The scientists had provided the brain, but the military had provided the armor. While these high-level deliberations were happening in offices, a different kind of innovation was happening in the workshops. This was the birth of the bazooka. For years, the army had been searching for a way to give a single infantryman the power to stop a tank. They had tried oversized rifles and heavy grenades, but nothing worked. They had the technology, but they had no way to deliver it accurately without a massive gun. The solution did not come from a clean-sheet design. It was a piece of industrial improvisation that would have been laughed out of a peacetime committee. Engineers took a simple, smoothbore steel tube and paired it with a repurposed rocket motor that had been sitting in a warehouse forgotten. There was no recoil because the blast simply blew out the back of the open pipe. It was a crude, ugly assembly that was exactly what the front line needed. Picture the reality for the man in the foxhole. This was not a precision instrument, it was a stovepipe with a trigger. One bazooka gunner crouched in a shallow hole in the earth. found himself facing the nightmare the army had been trying to solve for 20 years. A German Tiger tank loomed over him, 60 tons of steel mounting an 88mm gun that could kill a target miles away. The soldier did not have a sophisticated rangefinder or a gyrostabilizer. He squinted through a crude hinged bar wire sight that looked like something from a hardware store. He had to wait until the tank was almost on top of him, close enough to see the oil stains on its armor, before he pulled the trigger. The rocket did not rely on speed to kill, but on the chemical energy of the shaped charge it carried. When the launcher fired, it sent out a projectile that did more than strike the Tiger. It burned a hole through the thickest armor. This was the moment the hierarchy of the battlefield shifted. A $10 pipe had just neutralized a $1 million tank. This was where the bureaucracy finally caught up to the war. The army stopped waiting for a perfect anti-tank gun and embraced the crude reality of the man-portable rocket. They realized that in total war, a sophisticated theory is useless if a single, terrified man cannot carry it into the mud. The partnership between the scientist and the soldier had finally produced a weapon that was both brilliant and brutal. The monster was finally vulnerable, but the crisis of the front line was mirrored by a crisis of production back home. By 1941, the slow pace of the testing grounds had been obliterated by a single piece of paper. A presidential directive arrived at the desks of the supply chiefs, demanding a staggering 1,000 tanks every month. To understand the scale of this crisis, you have to realize that the nation did not actually have a dedicated tank engine. For 20 years, the military had failed to fund a power plant for armored vehicles, assuming they could simply borrow what they needed from the civilian world. But the civilian world was already at capacity. Heavy-duty diesel engines were being diverted to the Navy for submarines, and the best gasoline engines were reserved for aircraft. Tank designers were told to find their own way. This forced a period of frantic improvisation that turned the medium tank into a mobile laboratory for every engine that could be bolted into a hull. They began by stripping radial engines out of training aircraft. These were air-cooled monsters designed to spin a propeller in the open sky, not to sit in a cramped, armored box at the rear of a 30-ton vehicle. To make them work, engineers had to design massive fans just to keep the metal from melting. When the supply of aircraft motors ran dry, they turned to the automotive giants. One company proposed a bizarre assembly that combined 5 separate 6-cylinder automobile engines into a single unit. It required a maze of 68 spark plugs and a cooling system that looked like a plumber's fever dream. Think about the burden this placed on the mechanics at the front. In a single platoon, a sergeant might have 5 tanks that looked identical from the outside, but inside, they were entirely different machines. One required specialized aviation fuel, another ran on diesel, a third used standard gasoline. None of them shared the same filters, belts, or gaskets. The supply chain was choking on 5,000 separate spare parts just to keep the engines turning. The desperation of this moment was captured by the Ford mechanic. He was tasked with forcing a repurposed V8 aircraft motor into a hull that had been designed for a much smaller unit. The mounting points did not align, and the clearances were measured in fractions of an inch. Rather than waiting for a redesign from the capital, he took a sledgehammer and a custom welded steel bracket. He physically beat the interior of the engine compartment into a shape that would accept the new power plant. He forced the machine to work because the alternative was a factory line that stood silent. This was the success trap. The nation was producing tanks faster than any country in history, but it was doing so by sacrificing every principle of standardized maintenance. They were building a mechanical nightmare in the name of sheer volume. However, the engine crisis was merely a prelude to the catastrophe that awaited the crews in the fields of France. In the summer of 1944, the armored divisions moved off the paved roads and into the deep clay of the European countryside. The medium tanks, which had performed beautifully on the hard-packed sands of the desert, suddenly began to vanish. The problem was ground pressure. The standard tracks were only 16 inches wide, designed for the efficiency of a highway. On soft earth, the 30-ton weight of the vehicle was concentrated into a narrow strip of rubber, exerting 14 pounds of pressure on every square inch of soil. As the autumn rains began, the tanks did not drive through the mud. They sank into it until their bellies touched the ground. They became stationary targets for heavy enemy armor. The high-ranking officers in the rear suggested waiting for a new, wider track design to clear the factories back home, but the men in the mud knew they did not have months. They had hours. This is where the field crews shifted from the drawing board to the welding torch. They developed a field-expedient solution called the duckbill. This was a simple steel extension that could be bolted or welded onto the outside of the existing track links to increase the surface area. This was not a factory-sanctioned modification. It was a gritty grassroots effort to save the mobility of the entire force. The mud welder became the most important man in the battalion. In one instance, a technician spent 20 hours straight working in a freezing downpour, his goggles fogged and his hands numb. He bolted these steel extensions onto the tracks of an entire company. Every bolt he tightened reduced the ground pressure of the tank, eventually bringing it down to 12 pounds per square inch. It was just enough to keep the steel from being swallowed by the French clay. The ability to move across a muddy field, instead of being restricted to a single highway, allowed the armored columns to outflank the defensive lines. The final answer would not be found in a factory, but in a soldier's willingness to trust a machine he once feared. By the time the winter snows arrived, the good enough tank had achieved a level of reliability that the more sophisticated enemy machines could never match. They had traded the dream of the perfect machine for the reality of the one that kept moving. The army survived its own success. Think back to that morning in the North African desert, where a 2-pound shell struck a turret and simply fell away. That moment in 1943 was the low point of a 20-year failure, a scene where the theories of the boardroom were dismantled by the reality of the sand. But to understand how this story finally concludes, we have to look ahead 2 years to the banks of the Rhine. By 1945, the situation had changed. The soldier in the turret was no longer a victim of his own equipment. Consider the Pershing commander, a man who had spent the previous year watching his comrades struggle in machines that were undergunned and overmatched. He reached into the rack and pulled a 90mm shell into his lap. This projectile weighed 70 pounds. It was a massive blunt instrument of physics designed for one purpose: to punch through the thickest steel the enemy could manufacture. For the first time in the conflict, the man inside the tank felt the weight of a weapon that actually overmatched the threat outside. This brings us to the gesture that addresses the question of how this broken system finally found its footing. Inside that same tank, the skeptical gunner sat behind his sights. For years, men in his position had viewed the technological miracles from the home front with a mixture of fear and contempt. They had used leather straps to tie down the gyrostabilizers, those expensive boxes of sensors and motors designed to keep the gun level during movement. They preferred to trust their own eyes and a stationary hull. They didn't believe a machine could compensate for a bouncing chassis. But as his tank surged over the broken, muddy ground of the German frontier, this gunner did something his predecessors refused to do. He reached out and flipped the toggle switch for the stabilizer. He felt the 90mm barrel hum as the electric motors took hold, fighting the pitch and roll of the vehicle. The world outside was a blur of motion, but the crosshairs remained locked on the target. He didn't stop. He didn't wait for a stable platform. He fired a perfect killing shot while traveling at 15 miles per hour. The machine finally fit the war. To understand why this happened, you have to look past the steel and into the way the system itself had evolved. The broken bureaucracy of the interwar years had been a closed loop, a place where colonels designed for other colonels. But by 1945, that loop had been forced open. The laboratory and the foxhole were finally speaking the same language. The Weapons Bureau had learned a hard, bloody lesson. Combat feedback was more valuable than peacetime perfection. They had moved away from the 10-step standardization process that kept the best tools trapped in a basement for a decade. Instead, they embraced a system of battle trials. If a crew in the field welded a piece of scrap metal to their tracks to stay above the mud, that modification was sketched, photographed, and sent back to the factories in Detroit within weeks. The industrial team had stopped trying to build a universal machine that satisfied every manual and started building the specific tools the soldiers were actually asking for. The era of absolute design was dead. It was replaced by a modern research loop that prioritized the man over the bridge limit. The nation had stopped building for the parade ground and started building for the graveyard. If you visit a military museum today, you will see these machines cleaned and painted, looking like the products of a seamless industrial miracle. But look closer at a surviving 76mm Sherman or a heavy Pershing. A veteran tanker doesn't look at the scale of the hull or the horsepower of the engine. He looks at the small, rough, field-welded steel extensions on the tracks. He runs his hand over that scarred metal, remembering the day the engineers finally stopped guessing and started listening. That weld is the physical proof of the moment the bureaucracy broke its own rules to save the men in the mud. The magic wasn't in the box, it was in the realization that the soldier was the only expert who truly mattered. If you or someone you know has a connection to this history, the crews, the mechanics, or the families who saw these machines come home, we would love to hear your story in the comments. The specific memories that only the people who were there can provide are what keep this history alive. We have many more stories to tell, and we would be honored if you joined us for the next one.